I'm very happy to welcome Dr. Louis Vandenabeele and Dr. Clemens Knobling to speak to us today about 18th and 19th century Swiss timber bridges and roofs using laminated arches from the Grubenmann Brothers to Hetzer. Dr. Louis Vandenabeele is a postdoctoral researcher and teaching assistant at the Institute for Preservation and Construction History at the Federal Institute of Technology in Zürich, Switzerland. He graduated in architectural engineering from the Vrije Universiteit of Brussels and completed his PhD at the Vrije Universiteit Brussels on timber roof construction of the 19th and early 20th centuries in Belgium. Louis's current research projects include the 13th century Basilica of St. Anthony in Padua, Italy. Dr. Clemens Knobling studied architecture and business administration at the Technical University of Munich, and he completed his PhD there on historical timber roof structures destroyed during World War II in the city of Munich. He is also a senior researcher at the Institute for Preservation and Construction History at the Federal Institute of Technology in Zurich. Clemens is currently coordinating a state-funded research project on historic timber bridges in Switzerland's circumalpine region. Switzerland boasts a one-of-a-kind legacy of historic timber bridges and roofs. Today's talk will unravel the story of laminated timber arches, an enduring technological marvel widely represented in the alpine landscape. Louis and Clemens will begin in the late 18th century with the iconic covered bridges crafted by the visionary Grubenmann Brothers. From these beginnings, they will explore the intricate lamination techniques that thrived across Switzerland during the 19th century, enabling the creation of arches with spans of up to 60 meters. Woof, wow. Widespread laminated arches also found their place in roof constructions across Europe during the 19th century. Louis and Clemens will shed light on knowledge transfer through travels and treatises, drawing on Swiss and international examples. Their talk will finish in the early 20th century with the early use of glued laminated timber in Switzerland, illustrated by numerous still-standing examples, including the recent discovery of a Hetzer construction near Zurich. Exciting. Okay, over to you, gentlemen, Louis and Clemens. Thank you.
Thank you very much, Nick. Thank you. Thanks for this invitation and for this very complete introduction. We're really happy to be here and to see so many people online, although it might be very late or very early for some of you. To give you a bit more of context, so we are indeed working at the Institute for Preservation and Construction History at ETH Zurich. This is our chair, led by Stefan Hetzer, here on the left. And to give you an idea of what we are doing here, so this is an overview of our projects in Switzerland, in Italy, in France, Austria, Germany, and Sweden. But today we would like to stay in Switzerland, in stunning landscapes of mountains, rivers, bridges, and lakes and forests. Here you can see our campus, and we are now sitting in this building here in front. And we will focus on the incredible Swiss timber heritage, which was not damaged by the wars of the 20th century, which makes Switzerland a unique location to look at old bridges and roofs. And in particular, we would like to draw your attention to this technological feat, which consists of making curved elements out of straight timbers. And we find such laminated arches all over Switzerland in bridges and roofs. So Clemens will now start with the bridges, and I will continue with the roofs.
Thank you, Louis. So you expect me to say something about timber arch bridges, and I'm showing you this bridge here with a simple trestle in the middle. So don't worry, I will not start from zero, but yeah, this picture helps me to speak about the actual construction task. Why would you build a bridge with a wooden arch? Doesn't that sound a bit absurd to make an arch out of wood, a material that is essentially linear, especially before Otto Hetzer invented the laminated beam? We will hear of that, more of that later. Yeah, one reason is the danger of floods and ice. You can imagine this here. The more the piers are in contact with the water, or the more piers are in contact with the water, the more the bridge needs to be maintained and the greater the risk of collapse due to floating debris and ice, for example. The piers of the bridge shown here have had to be rebuilt several times since the 16th century. An arch would be a structure to span the whole river without any intermediate support. Another reason might be the complexity of timber joints. The greater the span, the more complex the structure, and the more timber joints need to be designed and incorporated into the structure. Please keep the complexity of this bridge, the famous one in Schaffhausen, still without an arch, built by Hans-Ulrich Grubenmann in 1758. Keep this in mind. Because less than 10 years later, the same master builder built a bridge in the nearby town of Wettingen that had the same free span as one of the openings in Schaffhausen, around 60 meters. But it was constructed in a fundamentally different way. Instead of a complex multi-layered structure, the main element is now here a solid, true arch to which the king posts supporting the roadway are attached. I don't know if you can see my cursor. Here is our rigid arch, the king posts, which are carrying here the roadway of the bridge. And please also keep in mind the arch of these kind of bridges is always on top of the roadway, sometimes leading directly to the abutments, and sometimes also working as a kind of bowstring structure when the arch is here fixed to the tie beam. Jean-Charles Kraft shows this bridge here in this depiction, which was published in 1805, 6 years after this bridge was destroyed in a war. So this bridge is not existing anymore, it was destroyed in a war. But did this bridge really look like this? We don't really know, especially this vertical folds look a bit suspicious. Keep that in mind. When you see this depiction here, which is a drawing by Johnson, he shows here these folds fixed in a radial way, which is maybe more likely. But on the other hand, he himself, or the engraver, here did not care so much about the interlocking of these arches. You see here these toothed structures. And there is a third source of this bridge, a model designed by the builder Grubenmann himself. It shows another picture. If you look at the elaborate wind bracing here and the complex roof, you might already assume that also this is not representing the real bridge, and indeed it was model built to present the idea of an arch bridge to the abbot of the Wettingen monastery, who was the one who paid in the end for this bridge. But what is for sure is that development begins here and reaches already a significant peak. And if I say it is beginning, or it was beginning here in Switzerland, then this is of course not completely true. The idea of building arch structures in wood is quite old. One of the oldest depictions of such a structure can be found already at the Trajan's column in Rome. You can see it here on the left side, which is showing a bridge with timber arches here supporting a roadway here with these trusses. And in the 16th century, here on the right side, you see a depiction of Palladio. He shows another popular idea, a trussed arch, which is imitating the principle of a stone bridge by assembling these trusses like wedge-shaped stones. Also, the idea of the massive arch, which is the subject of the following slides now, with bridges, is also older, but never really, or did not really mature at the time. This drawing by Fausto Veranzio from 1595 must therefore be regarded as a curiosity. But what he does take into account is, however, that the two layers of the arch should be joined together in a shear resistant manner, even if this type of production, like a jigsaw puzzle piece, would entail a high consumption of wood. And we also don't want to ignore the fact that the idea of the wooden arch had first breakthrough in the 16th century when we think of Philibert Delorme, for example. But yeah, here you see his invention on the left side in the depiction from himself, or here from Kraft, 1805. But yes, as I said, we are confining ourselves or limiting ourselves to the massive arch made of bent beams, not of stone boards. This map here shows the locations of the remaining historic timber bridges with real wooden arches. You can see that they were all built in the 19th century. There used to be twice as many, but most of the 18th century bridges have not survived. All of them have not survived. Some were down, others were sacrificed to car traffic. Nevertheless, there are still 8 of them in place with a remarkable cluster in the Emmental Valley here in the in the center of Switzerland. The surviving bridges show 2 different types of timber arches. Those with interlocking layers, as you see here on the left side, and those with non-interlocking layers, as you see here on the right side. The lamella of the interlocking arches show a saw-like structure, each interlocking on both the top and the bottom with the next lamella. In the case of interlocking arches, the oldest is the well-known bridge of Wettingen, already introduced, and the oldest one with non-interlocking arch was the bridge of Mellingen, also already destroyed. Mellingen was built 30 years later than Wettingen here, in 1794 by the master builder Hetzer from Luzern. We could call him the doyen of the non-interlocking arches. We didn't find an older example than the one of Joseph Hetzer. Interesting is that the seemingly complex interlocking arch is older than the non-interlocking arch. In fact, it turns out that the latter may have been a simplification, but it does not have the durability and monolithic effect of the interlocking arch. We will see this with another example on the next slides. But first, we want to lift ourselves up to take a broader view of the global context. We see that the oldest bridges that we can still trace are in Switzerland. Here, Wettingen, already shown, and also Mellingen, still from the 18th century. The reasons for this were explained by Louis at the beginning. By the way, the red ones here are the ones still existing. You can see that it also starts in France, in Germany, and also in the US at the beginning of the 19th century. Was there a question? No. At the beginning of the 19th century. A famous builder in this context, for example, is Carl Friedrich Wiedeking from Bavaria. Obviously, they all built the arches below the roadway of the bridges, whereas in the Swiss examples, as I already said, with one exception, the arches are always above the roadway, supporting it with the help of king posts. Let's have a look at some contemporary examples from outside Switzerland. Here you can see the famous Pont de la Cité in Paris from 1803. This was then also destroyed and rebuilt in more or less the same way shortly afterwards. What you can see here is a non-interlocking arch composed of 4 layers of bent beams below the roadway. And as you can imagine, this is then a disadvantage for the durability of this bridge, because this arch here is not really protected from the rain. Yes, there is a cladding on the sides, but the water can still drop from above on the arch and keep it wet, so to say. Another famous example is from the US, in this case, is the Colossus Bridge near Philadelphia, which had a span of incredible 340 feet. Also here, the Colossus Bridge shows the arch open. It is not really protected. It is below the roadway, which makes it difficult to maintain these bridges, this kind of bridges. But we want to limit us the Swiss examples today. So let's get back and have a look at this overview here. You see here the preserved Swiss timber arch bridges, or no, you see just the preserved arches of these bridges in these drawings. They are all shown in the same scale. So you can see here the difference from these very tiny bridges, like the one here in Grisons, Graubünden, the very east of Switzerland, to the biggest one in the Emmental region with a span of 60 meters. So from 20 to 60 meters. 2 bridges have a non-interlocking arch. The rest have interlocking arches. Next to these arches, you see, if you can see it, the members of each arch. We have shown them here separately. And you can see a big variety in size and also in the degree of curvature these members have. The process of bending will be explained in some slides later. And another aspect which might be interesting, we just have one bowstring arch which is attached to the tie beam, not shown here. All the others directly go from one side to the others to the other side directly to the abutment. I will now show these bridges in a few pictures. First, the non-interlocking arches. A famous example is again built by Josef Ritter, the master of the non-interlocking arches, the Spreuerbrücke in Luzern, a touristic hotspot. It has a span of 25.6 meters and is composed of this non-interlocking arch composed of these members which are shown in different red colors here. And here you already see the problem of this kind of non-interlocking arches. The lamellas are not really fixed, and that's here you can see a hole, so to say, in the bridge. The sun is shining through the arch, and this is a bad sign. The arch is not really working anymore as a monolithic structure. There is no more or not enough friction in this arch to be as rigid as it should be. This is no problem here in this case. It's just a small bridge with a span of 25 meters, and there is no heavy traffic on this bridge. Just it's just open for walking. So this might not have been become a big problem here. It's a bit different in the next example, also a non-interlocking arch by Josef Ritter with a bigger span of 31.7 meter, also above the river Reuss in the town called Sins. You can see it here. Just one part of the bridge has a real arch. And if you see the structure here, it's a multi-layer arch, non-interlocking, but you can see it is reinforced by an additional truss, because also this arch was not really working anymore, especially not because of the heavy traffic on this bridge. Also, before the cars came, this bridge was used for heavy loads, and this not very rigid, not very stiff arch was not enough here. Now we come to this, as I said, we just have two bridges with non-interlocking arches. I come now to the interlocking arches. Our single bowstring construction here in Grubenmann, with a span of just 20 meters. You see here very short members of this arch. It's also just two layers, and all these members have a butt joint directly in the middle of the king post, but it is still a continuous arch. You also have arched beams which end left and right of the king post. Then we wouldn't call this a true arch bridge, but here it is really a continuous arch interlocking. A very tiny bridge, but very beautiful with this nice landscape around it. But then they become really big. Next example is the Brunnwartbrücke, heavily restored and also translocated. built in 1837 and translocated in 91 with a span of 35.6 meters. You see here the 4-layer interlocking arch, and more or less the same structure you can see in our next example, the Orbenbrücke, also in the Emmental region, like the Hummerbrücke before, built in 1835 with a span of 41.3 meters. And you may have realized that there is a longer break in building arch bridges. We are now in the year 1834, and the bridges I showed before were around 1800. Maybe there were some more arch bridges in the meantime here in this region, but there was a big flood after, no arch bridges, but there was a big flood in the 1830s. I don't know exactly when, but this big flood swept away all the existing bridges at this Emme River, and only this one here survived. And this was already standing when this big flood came, and maybe this was then the role model for other arch bridges in this Emmental region. Like, for example, here you can see it in a photo, the 4-layer arch. This is really one of the most beautiful examples of an arch bridge. And this here was then also built, maybe the bridge shown before was the role model for these following bridges then in the Emmental region, which survived this big flood because of this one rigid structure, which is not touching the river. And this is the Schüppachbrücke in Siegnau from 1839 with a span of nearly 50 meters, which is still carrying lorries with a weight of up to 28 tons. Yeah, but you see here this arch was heavily reinforced. I marked the original arch, and all structures you can see below are the reinforcements. And finally, the biggest one in the Emmental region, again, the Wintersee-Brücke in a town called Hassel, also from 1839. The span is 59.5 meters. And this is really impressive. You see here a 7-layer arch, and also the structure here below are arched. You can see additional arches in the roof. So the arch is really the successful structure then in the Emmental. There was another bridge called Zollbrücke, which had the same span, but unfortunately also this bridge burned down. And this now is the biggest surviving timber bridge, historic timber bridge in Europe. So now you have seen all the existing bridges. Now let us think about how these bridges were designed. This was the case for all bridges. First, the builders, the master builders, had to build scale models. Here you see a nice example of a working model. If you look on the left side and compare it to the right side, you see different structures. You can really see how the master builder was thinking about the structure he really wants to implement using this model. By the way, this model shows a bridge which is not existing anymore, also in the canton of Graubünden, Grisons, a bridge in the so-called Versamer Tobel by a famous bridge builder called Richard Lanica. Unfortunately, all his bridges disappeared. This is from 1826. This model is still preserved in the museum in Chur. And they used models for the design process. They also had to build models to present it to the council who paid for the bridge in the end to convince them of this structure. This is a nice example of another arch bridge model, the bridge of Bischofszell. Also, this bridge is not existing anymore. And there you see that also these models can be very useful and important last witnesses of such incredible structures. After having built a model and getting the commission, the erection process could start. The most crucial part is bending the beams. What you can see here is a depiction of Carl Friedrich von Wiebeking, so a contemporary source from 1814. He shows how it worked. We assume that it wasn't done with steam in Switzerland, as in the French literature, for example. The French literature mentions also bending beams with steam. Here we guess in Switzerland it was bent cold, like Wiebeking shows here. This means that the beams were placed on a formwork and cooled down with wines. The beams had to remain in this position for a few weeks until they didn't bend back too much. A certain amount of back bending was okay, as we will see in the next slides. The already mentioned engineer Lanica proposed to not build a formwork like here, but just to erect two trestles and lay the beams on top and weigh down the middle by a random material from the construction site. Also this worked. And when the beams were bent, the erection process could start. First, this is how we guess the teeth were made for the interlocking arches. So the bent beams were laid on each other. Then they took a ruler to draw the lines of this of these teeth, and then they were sawn. And if you then assemble them, it fits on one side, but on the other side you have these gaps. And this is what we think are these wedges used for, to fill on the one hand these gaps, and of course to, on the other hand, to make this whole arch more rigid. Yeah? But it does not need to be so exact when you still have these wedges, one wedge from each side, to make this joints here, then to fill these gaps, these joints, and to make the structure rigid this way. So let's continue with the assembly process. We guess that they always build a scaffolding in the water. We assume that it is not possible to do this without a scaffolding. And there are also contemporary sources which show these kind of scaffoldings. Here also in the case of a timber arch bridge, this is a publication from Prague. So you see this was a whole European topic. On this scaffolding, then the lower parts of the bridge could already be assembled. By the way, this 3D model shows the biggest of all arch bridges, this Wintersee bridge, the last one I showed, which is still existing. In the next step, you could erect these king posts. The king posts are always composed of two identical parts, one on the outside, one on the inside, and this tie beam in the middle, and also the arch in the middle of these two parts of the king post. And here those king posts already erected could be used also as a kind of false work for the timber arch. As I said, the beams were already bent, but they always bent back a bit. But using this king post as a false work and then putting the members of each arch here in this open timber joints made them stay in place, and then they were really fixed and could build this rigid arch structure. Here the one colored in red is not yet fixed between or in this open timber joint, but the others already are. And so this works from one layer to the next until the arch is ready. Then the inner parts of the king post could be attached, and then also the beams which in the end carried the roof, the cross bracing, and yes, finally the roof. And also here they used these little, quite thin arches to carry the load of the roof to the sides, if this really works or not. And in the end, our scaffolding could be removed and the bridge was completed. You see here on the left side a historic picture of, again, this big Wintersee bridge. And I come now to my last point, the preservation of these bridges, or we call it sailing Swiss timber bridges. How were they saved? Most of them disappeared because they were not able to carry the load of cars and so on. But some of them were dismantled, and with this kind of structures, this is very easy. You can easily dismantle them, as you see on this right side picture and also on these pictures. And the dismantled parts of this bridge then were removed and brought to another place where they were assembled again. And that's why this bridge is now standing some 100 meters further down the river at another place.
So we now switch from bridges to roofs, and this transition is quite easy because some of our very famous bridge builders also built roofs. And as you can see, they introduced these longitudinal arches also in roofs. So somehow they built roofs a bit like bridges. Most of them are polygonal arches, but you can also see here on the bottom right this interlocking arch, so what Clemens would call the true arch in a roof at the end of the 18th century. If you're interested in this topic, there is a recent book by our colleague Jasmin Scheffer, which was printed just last week, so you can find this online. The reference is at the bottom of the slide. But the idea to build interlocking arches in roofs was clearly in the air at the turn of the 19th century. We find such roofs in many treatises, for example, here in the treatise of Emy. And Emy is responsible for the next milestone in this development. He invented and he built several laminated roofs in France and in Belgium. So these roofs consist of bent boards, which are assembled with iron bolts and iron straps. Emy was a military engineer, so most of these roofs are in riding halls, military riding halls. This is a side note, but quite surprisingly, two of these roofs are still standing today, and they're about 200 years old. You can find one in Bayonne in France and another one in Liège in Belgium. This is really worth a visit. after IMI, in the second half of the 19th century, this development continue, especially in England and in Germany. This could be an entire lecture, so we will not go into that. We will stick to our Swiss roofs, where a lot of very impressive roofs were built in the second half of the 19th century. And this is actually the topic of a PhD dissertation by our colleague, Kylie Husnack. So a lot of wide spans in timber in the second half of the 19th century in Switzerland, but not so much laminated roofs. We have just a few examples. For example, here on the right, the roof of this church in Lausanne. But here it's built with vertically placed boards, a bit in the Philibert Delorme way. So not so many laminated arches and roofs in Switzerland anymore. And we actually have to wait until 1906 and the patent of Otto Hetzer, carpenter and sawmill owner in Weimar in Germany, who patented this glued laminated timber. Of course, he was not the first one to use glue to attach boards together, but he's really the one who managed to advertise this as an engineered material and as a cheap alternative to iron structures. And this worked very well. Very quickly, he built a lot of structures in Germany, but also abroad, especially in Switzerland, where as early as 1908, so only 2 years after, the engineering office of Terner and Chopard, based in Zürich, bought the patent of Hetzer. And in 1912, they formed a corporation of contractors who were producing and using the Hetzer system all over Switzerland. Again, this story can be discovered in details in the PhD of Hoshanak Haddadi, which is available online on the research collection of ETH. Terner and Chopard contributed significantly also to the development of glulam with a lot of material research and load tests. For example, in this paper by Chopard, you can see, it's a presentation of the results of load tests carried out in 1912 before the construction of the railway hall for the Swiss railways, the SBB. And the first glulam roof in Switzerland was built already in 1910 in a military riding hall in St. Moritz by Terner and Chopard. And in the following decades, they built all kinds of structures. So this is this storage of the SBB, but also factories, gyms, temporary structures like sentries for bridges. Here, a temporary shelter for planes, airports, and so on and so on. So glulam was so popular in Switzerland that hundreds of structures were built in the 1910s and 20s. Today, there is no inventory of these glulam structures, and actually we still discover them from time to time by chance. And the good news is that, like for the bridges, many of these roofs are still in place. So to end our journey, I would like to show you a few examples that we have visited and surveyed, or that have been surveyed by our students. So the first one is the oldest one, the first glulam roof built in Switzerland. It's this riding hall in St. Moritz, and as you can see, it's still in a quite good shape. It has been reinforced over the years. So you can see here the arches, which are composed, the entire structure is composed of 4 segments assembled at the top with the king post, with some iron struts, and here this level with some iron plates and bolts. So here are some details of these iron plates. What's also remarkable is that all the rafters are in glulam because they are curved, as you can see here. So all these elements are also in glulam, and some of the purlins are also consisting of glulam elements. So very nice and very early example of the glulam structure. The second example is 10 years younger. It was built in 1920. And actually, we found this by surprise a few months ago. I mean, by chance, in an old staircase factory in Baden. You can see that they really trusted the glulam structure because the arches are supporting this crane that can carry 5 tons. And this crane is rolling on some glulam beams. So this is how it looks like. Interesting detail also is that this glulam structure, and unlike many others, was built on an existing building, which doesn't have a rectangular floor plan. And so the span is continuously changing. And to cope with that, they had to cut the prefabricated arches at the top. And because of this, the ridge of this roof is not horizontal, but yes, going down. You can also see some carpenter's marks. This is also typical of all these glulam structures. They are still full of carpenter's marks. Here are some details. So this is the typical assembly at the top with a king post, some iron straps, and most of the connections are done with iron bolts. Here you can see a nice carpenter's mark. Again, in this roof, all the purlins are in glulam. And we move to our last example, this riding hall in Wetzikon from 1927. Probably the most elegant example because this is not a purlin roof, so you have only these glulam elements, which are very, very slender and assembled at the top with this tiny king post and a little collar. So a very simple and elegant structure in Wetzikon. And again, some details. The assembly at the top, carpenter's marks. So it's really a very nice mix of craftsmanship and timber engineering. So I hope that you enjoyed this journey from bridges to roofs in Switzerland. And Clemens, I give you the final word.
Thank you so much, Louis. Yeah. As Louis already mentioned, there is now a research project ongoing in our chair here at the Institute. And that means that new findings and insights on all kinds of historic timber bridges will be published continuously. And if you have questions concerning this or whatever, don't hesitate to ask us now or by email. And if you are interested to visit timber bridges yourself or many other exciting structures,
like glulam,
here in and around Switzerland, and to exchange with colleagues from construction history, you can meet us next June at the 8th International Congress on Construction History, 8ICCH, here at ETH Zurich. Thank you.
Yes, thank you very much.